Hi everyone and welcome to the show. Today we have Lorcan Conlon with us, who will be talking about collective measurements within quantum computing. This was a super interesting discussion and we actually looked at the paper during the discussion as well. If you're interested in checking that paper out, I'm going to link it in the description and you'll also find the contact details to Lorcan there. So without further ado, please enjoy the discussion. Lorcan, thank you very much for joining today.
No, nice to be here. Thanks for having me.
So, yeah, sure. So I read your paper. Specifically, we're going to be talking about approaching optimal entangling collective measurement on quantum computing platforms. And I figured to kick that off, maybe we could give a very brief introduction to the field that this actually applies to, so quantum metrology. Just very briefly, we'll get into the details of the subject, but for anyone listening who's not very familiar with the topic.
So quantum metrology is basically asking the question, how well can we measure some physical object? So, for example, if I take a beam of light, it could even be the light coming from the sun, that light will have a certain brightness or intensity, and that basically translates to a property of the photons or the electromagnetic wave that's coming towards you. And so, normally, a really basic measurement that we can do of, for example, light is we look at it. Our eyes are basically photodetectors. And so our eyes sense light and they can detect when, oh, it's really bright or it's really dim. And that is a really basic measurement. And what we try and do in quantum metrology is use techniques from quantum mechanics to make even more precise measurements. So quantum metrology sort of has two sides to it. On one side, the theory of quantum mechanics actually places limits on how well we can measure something. And this is the sort of famous uncertainty principle, which I think we'll get into at some stage. And on the other side, then the techniques from quantum mechanics, which are entanglement and squeeze light and other such things, these let us make better measurements than are possible classically. So, sort of in brief, it's trying to measure things as accurately as possible.
Hmm. And these kinds of measurement techniques, where you actually leverage the quantum mechanical aspects in the actual measurement, how long have they been sort of used widely? And are they used in industry applications right now, or is this mostly a research field at this point?
It sort of depends where you draw the line of what's quantum mechanical and what's not. So there's, for example, a quantum mechanical description of a laser, and lasers are now used in everything basically. Your barcode at the supermarket, all sorts of um, everyday items use lasers, and that sort of really basic aspect of quantum metrology is used every day. But the more advanced and more sort of recent developments focus on using entanglement and squeeze light, which are like super sensitive properties of quantum mechanics. And it's really hard to bring that out of the lab into the everyday world. So, for example, in our lab, we have a lot of squeeze light sources, and these they involve really big optical tables, and basically it involves us taking a laser, putting it through a crystal, and measuring the output light. But it's really sensitive to any loss or any noise, and so it's really hard then to take that and put it out in real life, where it would be moving around all the time, and there would be people walking by, all sorts of noises, everything just would damage that and sort of lose the quantum sensitivity. So for now, it's mostly in the lab, but there are some real world applications. So I don't know how many people will be familiar with gravitational wave detection, but the gravitational wave detector in America, LIGO, has recently used quantum mechanical properties to get a better sensitivity than is possible otherwise.
Hmm.
So a bit of both.
Okay. Yeah, okay. No, that's a good answer. So maybe a small detour actually to what we're going to discuss. I think you mentioned the infrastructure that you have at your lab right now, and part of what you did in this investigation is to actually compare different infrastructures and how well they're able to measure these, well, the details of which we'll get into in a little while.
Yeah, yeah.
Can we just take a small detour and talk about the equipment you have at your disposal and how you sort of set up this experiment? Because you're leveraging superconducting quantum computers, you're leveraging trapped ion ones, and you're also leveraging photonic systems. So Could you describe which ones you have at your disposal, which ones you sort of outsourced for this project, or how that infrastructurally worked?
So there are a few different sort of brands of quantum computing. Not brands is the wrong word. Different like large scale structures of quantum computing. The most common one that you hear of in the news, basically it tries to take the direct classical analog of a bit and map that to a quantum bit or a qubit. Um, and that is the superconducting trapped ion and photonic devices that we used in this experiment. So, funnily enough, the devices and the equipment that we have access to in our labs actually fall under a different structure of quantum computing called sort of continuous variable quantum computing, which isn't as mainstream. And we actually didn't use the resources in our own labs for this. And the reason for that is that we came up with this theoretical proposal and we realized that it maps to the first style of quantum computing, but it doesn't map to the second style that we had access to. So for this experiment, we outsourced all of the quantum computers. We derived the theory in our research group at the Australian National University, and then we spoke with collaborators in America, collaborators in Austria and in Germany, and we got remote access to their quantum computers. So
Okay.
from our side, the hardware was all outsourced.
Right. I want to get back to that point later when we actually start talking about error correction in particular. But for now, then that I think helps set the stage. So if we get back on track with the measurements that you were actually doing, part of this is investigation of various boundaries like that exist in terms of how accurate your measurements can be, as you mentioned before. There are a number of these being referenced in the paper, so I won't try to pronounce them all, but like Holevo and Nagaoka and
Congratulations. Yeah.
so forth. Yeah, exactly. When it comes to these bounds, are they all direct derivatives, let's say, of the uncertainty principle, or is there something else also at play for this?
Um, I would say they're not direct derivatives of the uncertainty principle. So the uncertainty principle, as it's normally formulated is if you want to measure something, one physical quantity more accurately, you have to measure some corresponding physical quantity less accurately. And that's commonly described as the position and momentum of, for example, an electron. So that basically says if I take the product of the uncertainties, there's a limit on that. But the quantum metrology bounds that we were looking at in this paper, they actually apply even if I'm only trying to estimate one of these parameters. So if you go back to the uncertainty principle, by making my uncertainty in the measurement of the electron's velocity arbitrarily large, I can make the uncertainty in the measurement of the position of the electron arbitrarily small. And so in that sense, the uncertainty principle, if I'm only measuring a single parameter, doesn't place any restrictions on how accurately I can measure that, whereas the
Mhm.
bounds we use in this paper do. Now, in the paper, we do consider estimating multiple parameters, and so you can essentially map that to the uncertainty principle, and that was done by other scientists, and we did compare the Halevo and Nagaoka bounds in our paper to alternative bounds that are derived directly from the uncertainty principle. And as we actually saw then in our paper, there is a slight difference between the two.
Mhm. So, do you have a conceptual explanation of where these bounds arise from? So, if they're not arising directly from the uncertainty principle, and maybe this is a tricky question to actually answer, but is
This
there
is a
something
tricky.
else that they naturally map to, a
Yeah,
fundamental
I
law that
mean,
tells you? Yeah.
in my opinion, that there is a place where they naturally come from, but I would like to stress that lots of different researchers would say would give a different origin for it. For me, it's all about the well, everyone will broadly agree, but they might have a different way of phrasing it. But for me, it's
Mhm.
about the probabilistic nature of quantum mechanics. So one of the reasons quantum mechanics has become so mainstream is quantum computing, and one of the ways that quantum computing is normally explained is that a quantum bit doesn't have to be a zero or a one. It can be some sort of mixture of zero and one, and you have this certain probability of it being in the zero state and a certain probability of it being in the one state. And because of that, quantum mechanics is sort of inherently probabilistic. So if I measure some random quantum state, there's a probability I'll get some measurement outcome, a probability I'll get a different measurement outcome. And whenever you're measuring, and so sorry, whenever I'm because the different outcomes are drawn from a random probability distribution, there's essentially going to be some uncertainty in how well I can measure a quantity. So, for example, imagine I give you a perfect coin. So if I flip the coin, there's exactly 50% chance that it's tails and exactly 50% chance that it's heads. Now, if you flip that coin 10 times, that does not mean that you're going to get five heads and five tails. Even if it's a perfect coin, you might still get six heads and four tails, or vice versa. And so, if you're allowed to flip this coin 10 times, and then you have to estimate how biased it is, if you get six heads and four tails, you would guess the best guess you can make is that it's 60% biased towards heads. And so, because you're sampling a probability distribution, there is essentially some error on how accurately you can measure the properties of that probability distribution. And quantum mechanics, with its inherent probabilistic nature, then this means that when we try and measure some physical property of a quantum system, we're essentially sampling from a probability distribution. And so there has to be some uncertainty. Maybe that's a
And so,
long-winded explanation, but that's how
okay.
I think of it.
Yeah, yeah. No, I think it's a good explanation. My follow-up question on that would be, for these bounds then, are all of them related to the number of samples that you take? So in practice, you could repeat your measurement an infinite amount of times.
Yeah.
Assuming you did that, would all of these bounds go to zero?
Yeah, that's exactly right. So all of the different bounds that we give sort of correspond to different measurement scenarios. So they essentially give a coefficient, and that coefficient then, if I repeat my measurement n times, the uncertainty goes as that coefficient divided by n. And so you're exactly right. The variance, or the standard deviation in the measurement squared, goes as 1 divided by the number of samples. And so if I have enough samples, that will tend to zero. And
Okay.
so one important question in quantum metrology is, how fast can we scale to zero? And the question that we addressed was more, how small can we make that coefficient? So for our
Mhm.
work, we actually don't care about that number of samples, because we normalize everything to the same number of experimental repetitions.
Mhm. And roughly speaking, again, a small detour, how many repetitions would you do
So
for
for
the
our
different measurements that you
experiment,
conducted?
we did. Oh my goodness. Oh, sorry. Yeah, I remember now. We did 512 repetitions to get one error value, and we then repeated that error measurement 400 times. So in total, we had 400 times 512. So roughly
Right.
20,000.
Okay. Sorry to put you on the spot on that as well. I just wanted to
No,
get like
no, you're
a
okay.
brief sort of brief conceptual view of how many measurements you actually
Yeah.
did. But I think it would be natural then to maybe go from where we are now to extend this to the concept of collective measurement. So collective measurements is the term that you refer to a lot in the paper. Would you mind just defining that,
Yeah.
at least as far as this paper goes? It doesn't need to be a very formalistic definition.
So yeah, I mean, as you say, the whole idea of this paper was we were comparing collective measurements to separable measurements. So collective measurements try and make use of one of the quantum mechanical properties that I mentioned earlier to enhance the sensitivity, and that property is entanglement. So imagine I give you 1,000 qubits to measure, and I tell you that all of these qubits have the same information encoded onto them. Then one very simple measurement strategy that you can do is you can take the first qubit that comes in, measure it, write down the result. Then take the second qubit, measure it, write down the result, and so on and so forth. A collective measurement goes beyond that. And what we did in this paper was we took the first two qubits, entangled them, and then measured them both at the same time and wrote down that result. And we did that 500 times to use, say, all 1,000 qubits. And by doing this, we get a better sensitivity than if we measure the 1,000 qubits individually. And you can go again, you can take three qubits at a time, entangle all of them, measure them all together, and then write down that result and repeat that 333 times. And we actually did try. So in this paper, we investigated measuring qubits one at a time, two at a time, and three at a time. And what we found was that the two qubit measurement performed best, even though in theory the three qubit measurement does perform better. The devices that we were using are sort of these near, not like they're noisy devices right now. They're not the future quantum computers that we will have. And so the three qubit measurement was just too complex for where we are now. So yeah, roughly collective measurement tries to use entanglement to get a better measurement sensitivity.
Hmm. Putting all the practical aspects of performing a measurement like that aside, what is the reason why entangling two or three or more qubits, like you described, actually is able to produce more accurate results in the first place? Do you have
Um,
a way of explaining that?
I do have a way of explaining that, but I would like to say that I've just done nearly a 5 year PhD in this topic, and by the end I was still confused um, about the question, because this question, it really, like, to me it is a bizarre question. Somehow I'm receiving these 1,000 qubits and the information's encoded onto them, and somehow by measuring them together I get more accuracy. And the reason, so there are multiple ways of thinking of it. The easiest way of thinking about it, which perhaps doesn't provide much intuition, is simply that by performing this entanglement and measuring the qubits two at a time, I can reduce that statistical uncertainty that I was talking about earlier. So basically, the uncertainty in measuring the qubits comes from the fact that when I measure the qubits, I'm drawing from a random probability distribution. When I take two of these probability distributions, i.e., two qubits, and entangle them, I basically can use the correlations that are generated in the entangling measurement to reduce some of the statistical uncertainty when I draw from this random probability distribution. So essentially, I can, rather than drawing from the same random probability distribution twice, I can take the two samples that I have from the probability distribution, mix them together to get a new probability distribution with reduced error compared to the two individual probability distributions. One other way of
Mhm.
thinking about this, which is more intuitive, is that, okay, this is a bit of a detour. When I measure a qubit, I get either a 0 or a 1. When I measure two qubits, I can get 0 and 0, 0 and 1, 1 and 0, or 1 and 1. So I've went from two
Right.
measurement outcomes to four measurement outcomes. And when I measure three qubits, I then get eight measurement outcomes, ranging from 0 and 0 and 0 all the way up to 1 and 1 and 1. And so you can kind of think of this as a more fine graining of the measurement. As I go to more and more qubits, I'm sort of probing the distribution more finely, if that gives a wee bit of intuition as to why this works. But
Hmm.
yeah,
And
sorry, that's the best
and
I can offer.
okay, and when we have these multiple qubits as well, they would be normally placed in the same state. You would expect them to be all in state one. Let's say if we're summarizing it as like
Yes,
either being in the state zero or one, you would expect all of them to be in the one
yes.
state.
So
Let's say.
one of the sort of the conditions for doing this collective measurement is that I have identical copies of the same quantum state,
Hmm.
um, which sort of is a wee bit in contradiction to a famous theorem of quantum mechanics, which says that I can't copy a quantum state perfectly. Um, but that's different to not being able to make an IID, independent and identically distributed um, quantum states drawn from that distribution. So you can think of this as, I can, if you imagine your qubit as an atom, say, which is either in the ground state or the excited energy level state, I can initialize many of these qubits all into the ground state. But that's not the same as if I give you a single qubit and it's in the ground state, you have to copy it without knowing what the qubit is. Because I know which qubit we're trying to prepare, we can then make individual copies of this, and then yes, as you say, all of the qubits are in the same state, and then we can perform this collective measurement.
Hmm. Okay. Yeah. So I want to get into the details of both this, like the fact that we cannot copy a quantum state altogether, and then also just the infrastructure associated with the measurement, also what the probe actually means in the context of this. But if
Hmm.
we, before going to the probe, stick to the concept you just mentioned of copying quantum states. So you're not allowed to copy a quantum state. Absolutely, I agree, and this is something I read up quite a bit on when I when I tried to formalize the questions around this. But um, as what you are allowed to do is you're allowed to prepare all your quantum states in the same way, thereby making the distribution that they follow identical. Can you say
Yes.
that, or is that also too
Yeah. No.
much of a?
No. That's correct. So we can
Okay, so they're
prepare quantum state.
IID, all of your
Yeah.
qubits, let's say, and statistically equivalent,
Yes.
but they're not actual copies of each other's states necessarily.
Yes. And the
Okay.
reason for the no copying theorem is because you it's more you can't copy an arbitrary quantum state. So if I tell you that I'm sending you this qubit in the ground state, then you can copy it because you just prepare two qubits in the ground state. It's more the fact that if I'm sending you an unknown qubit, which could be in the ground state, could be in the excited state, or could be in some mixture of the two, then you can't copy that because you don't know what I'm sending you. If that
Would
makes
you
sense.
ever would you ever be able to tell me that it's in the ground state with 100% certainty? I guess.
In theory, yes. I can make
Okay.
this state in the ground state with perfect um yes, in theory. The ground state
Okay.
exists, so to speak.
Okay. I'm
But
still, so that again makes me a little bit confused now. So I thought I had sort of a somewhat of a grasp on this, but that makes me unsure. So let's say we have two qubits. You're able to actually say that one of them is in the ground state.
okay,
How?
because of experimental
Yeah.
imperfections, I will never be able to say that. But
Okay.
I mean, in theory, we could say that, yes.
Then how come? Wouldn't that correspond to, let's say, a perfect measurement of a qubit? Nevertheless.
In terms of the probability distribution and the uncertainty that I was mentioning earlier,
Yes.
yeah. So again, say I give you this zero state,
Hmm.
and um, and I'm asking you, is this exactly the zero state, or is this the zero state and a tiny, tiny probability of the one state? If I
Hmm.
give you the zero state and you measure it 1,000 times, you cannot say with certainty that it's the zero state because it could be the zero state and one part in a million of the excited state. And you just
Hmm.
haven't, and I can claim, oh no, I didn't send you the zero state. You just haven't measured it accurately enough to tell me that
Hmm.
it's exactly the zero state. So, in terms of extracting information about an unknown state, you still don't have perfect uncertainty. But in theory, yes, I can prepare the zero state, and
Okay.
and there are some pathological situations where these uncertainties do go to zero, but they're not physically well defined. And the main reason they're not physically well defined is because, um, like I say, experimentally we can't make the zero state. It's always going to be. It's never going to be perfect.
Hmm. Okay. I think I see the distinction. Can we focus maybe on on the probe now as well? Like how
Mhm.
you actually not just set up the experiment in terms of putting multiple qubits in the same state, but how do you also measure that from a practical point of view?
Okay. So one of the devices that we use is a superconducting device. And so I'm not 100% familiar, but the zero state I think corresponds to the absence of a superconducting pair of electrons, and the excited state corresponds to the presence of a superconducting pair of electrons. And then using microwave pulses, the superconducting devices can manipulate the qubit into different states and can make the qubits talk to each other. And then at the end of the experiment, they read out, and basically the measurement is to check whether I have this superconducting a pair of electrons. The trapped ion is sort of similar. It uses energy levels of a different ion and laser pulses to address the different qubits. But from my side, because we had outsourced the hardware, um, we were, all of the calibration, the setup, the experiment is all built for us. We were essentially just programming the device to do what we wanted, and the way we do that was we tell the device we want to initialize all of the qubits in the ground state, and then we want to rotate all of the qubits by a certain amount. And that rotation was actually the parameter we were trying to sense in this experiment. So it is a wee bit artificial in our experiment, because we obviously we measured a quantity that was on a superconducting qubit in a lab in a really isolated scenario. So it's not like we were sensing some like physically relevant parameter, but it could have been like a physically relevant parameter. So, for example, if an external magnetic field had passed over the qubits that we were looking at, that could cause a rotation of the qubits. Now, again, yeah, in our experiment, we did the rotation ourselves, but what that rotation was attempting to mimic was some sort of external parameter that would cause this rotation. And then by measuring this rotation more accurately, we can measure the magnetic field more accurately, or the external parameter that's causing this change. And that's ultimately what we want to go, where we want to go with quantum metrology. Like, how well can we sense some useful external quantity? So yeah, sorry, back to our setup. We prepared all of the qubits in the ground state. We then rotated the different qubits by the angles that we wanted to measure. And then we decohered the qubits. The decoherence is a little bit funny. Essentially, we wanted to make our qubits less perfect so that our results could be better. I don't. That's not true. It's not to make results better. It's the benefit of collective measurements. It only becomes evident when your quantum states are not these perfect pure states. So we just had to make our quantum states not the perfect state that is. Again, it's not, you're never going to prepare the perfect state, but it's approximately a perfect state. So we deliberately decohered the qubits to get to the regime where collective measurements will help. So at this stage, what we have is we have an array of qubits which have all been rotated and decohered, but this has been done independently. So the different qubits are still completely uncorrelated. And then when we perform the collective measurement, we entangle the two qubits, and then we measure them both at the output. And our sort of contribution was to design the measurement that would optimize the information that we can extract from pairs of qubits. So basically, on our side, we first sort of came up with a physical problem where the collective measurements will help, and then we optimized the parameters of this quantum circuit. So essentially, after we had prepared the qubits and we started to correlate them, you have a bunch of free parameters which corresponds to how much you want to rotate different states, how much you want to couple them, all sorts of different things. And we optimized them parameters and then extracted the information as well as we could. So that was sort of the process.
Let me actually share my screen, because I have the window with your experiment set up, just so we can have a look at that at the same time. So you can see it now, right?
It is loaded. Yeah, perfect.
The first question I would have is with the decoherence. So you're talking about, this is section D now, so up here. We have this block sphere that represents the qubits, and then as you decohere them, you actually shrink the block sphere. Could you maybe give some intuition as to why that is accurately represented by shrinking the block sphere? So from my perspective, like when this was surprising to me, because when I read it, I would figure that you decohere them, and that sort of means that you're incurring some perturbation of your qubit that you don't necessarily know, so that you would have some uncertainty, but not necessarily that you would change, let's say, the radius of this block sphere, if you will.
That's a good question. So all of the points on the outside of the block sphere here, the larger block sphere, that's a sphere of a radius 1, and so all of the points on the surface of that correspond to this perfectly pure quantum state. So if I consider the point pointing perfectly up the z-axis, so the coordinate 0, 0, 1, that corresponds to the ground state, and that is the zero state, and the coordinate 0, 0, minus 1 corresponds to the excited state, which is the 1 state. So you can think of them as sort of opposite vectors that point opposite one another, and orthogonal vectors on the block sphere always point perfectly opposite one another. Now I can make a classical mixture of quantum states which is not a pure state. So if I make a classical mixture of the ground state, which is the vector pointing vertically upwards, and the excited state, which is the vector pointing perfectly downwards, what I do is I essentially add them two vectors together, and you can see them vectors will cancel out and give you a vector with zero length, which is essentially the coordinate 0, 0, 0. And that's a completely classical mixture of an excited state and a ground state, which is essentially a coin being flipped. It's either a heads or a tails. It's never this heads plus tails, which is what the quantum state can be. And so if I take this classical mixture, I get the coordinate 0, 0, 0. And so you can think of this coordinate 0, 0, 0 right at the center of the block sphere as being the completely classical state. And as you go closer and closer to the origin, then you go closer and closer to this completely classical mixture. And so in that sense, you could maybe think of, yeah, the closer to the origin I go, the more classical I am.
So let's say you're at, well, it probably does, but I also have some follow-up questions on it. So let's say you're moving to the origin, like you have this 3-point coordinate system, and well, how would you? Let's see. The only two states this could fall back on, like let's say you do a measurement, is what I'm trying to get to of this particular qubit now. The only two states it would be allowed to collapse onto when a measurement is onset is either +1 or -1 in this case. That's the only axis that it can collapse to. Because if not, then the question I have is, like, let's say you make it to the origin, then the block sphere from my perspective contains no information as to which state you will fall back on. And if you only have two states, like we were talking about with the coin flip, then that makes perfect sense. But could you ever have, like, if you have qubits that could fall onto multiple states, not just two, is it not even fair to model that by means of a block sphere like this?
No, it is, and actually all of the qubits can fall onto the measurements that we normally think of are we measure and we find either the ground state or the excited state, which is pointing up or pointing down. I can actually put a quantum gate right before the measurement, which essentially rotates the entire block sphere so that the x-axis points up. And then I still measure either the ground or the excited state, but because of the operation that I did just before the measurement, the ground and excited state actually correspond to the positive and negative x-axes. And I can do a similar thing, and so I can actually project onto any axis, any point on the block sphere that I want.
Mm-hmm.
Sorry, I kind of forget your question, but I remember when you asked, that was the thing I was thinking, that you can measure on any axes. What was the rest of the question? Sorry.
You can measure on any axes. My question is, if you have more than two ground states that your quantum state could collapse on when you measure, like in that kind of event, if you shrink your block sphere, I feel like you lose the information about which state you can collapse on, and maybe that's the entire point. Like if you have a fully
no, you're exactly right. That is the entire point. So this shrinking, because it's exactly the same no matter what axis I'm looking along, the information about any axis is shrinking, and so no matter what measurement I decide to do, I have lost the same amount of information, and the amount of information that is lost is proportional to how much the block vector has shrunk. Now you can consider different models which actually sort of squeeze the vector or the block sphere, so it becomes like a rugby ball nearly, and you can have these models which make it all shrink up to the top of the z-axis. So you can have different decoherence models which result in like an asymmetric loss of information about the three different axes, but the model we are considering was symmetric about all the axes. So yeah, like you say, you can project onto different states, and with this model you do lose information about all of them projections.
Mm-hmm.
As you shrink to the origin.
Okay, I think that makes a lot of sense. If we consider the let's say flow chart, if you will, for how information passes through the system. So we start with qubits on the left side. As you said, we perturbate these by some known amount in the beginning, and then we try to reacquire that information by means of measurement. And we compare that, I would suppose, then in the end here, when we construct our mean squared errors, we compare the intended perturbation of the qubit to the one that we actually measured in the end.
Exactly.
First of all, if there's anything you would like to add to that I got wrong, please jump in.
No, that's perfect. Yeah, we put in some rotation or perturbation that we know exactly, and we try it and measure it. So yeah, exactly.
Okay. And first of all, one question I would have is, how certain are we that the perturbation itself is not very error prone? Like, are you assuming in the experiment that you can perturbate these states with perfect accuracy, or are you actually taking that into account in your models?
No, that's a great question, and that does play a part. So this actually comes back to the scaling that you brought up earlier. The fact that if I use more and more qubits, I get a better and better accuracy, in theory. So let's just imagine a really simple example that I can implement that perturbation at the start to an accuracy of 1 part in 1,000. Then if I use 1,000,000 qubits to measure this uncertainty, I'm looking for an uncertainty that's 1 part in 1,000,000, but I can only actually encode the information with an uncertainty that's 1 part in 1,000. And so I'll never be able to measure that to 1 part in 1,000,000. So the accuracy with which we can actually implement this encoding ultimately does limit how accurately we can measure the device, or how accurately we can measure the perturbation. But if you look at, for example, circuit F is this 2-copy collective measurement that we implemented. So the 2 qubits come in, we entangle them, and we implement a series of quantum gates. These entangling operations are considerably more difficult than the rotations we use to encode the information at the start of the circuit. And so that measurement part of the circuit is actually considerably more noisy than the initial part. And so that essentially means that we won't ever hit this problem in this particular example. But yeah, if for some reason the encoding was particularly noisy, more noisy than the measurement circuit, then that would be a huge problem. We couldn't get the results that we get in this paper.
Mm-hmm. Okay, and just for me to understand the reason for this quantum circuit, so we said before we need to entangle the circuits very naively. Let's say you would just have a circuit that has one of these entangling operations for the qubits. Why is that not sufficient? What is the requirement or the need for putting in these additional blocks that we can see, like the U's and the R's in part F of this figure?
So the U's and the R's are single qubit operations, which are essentially just getting the 2 qubit states to be in the optimal state to generate the right amount of correlations. So I don't really have a great physically intuitive reason for this. We just numerically optimized this circuit, and this was the circuit that we got out with these parameters. And we knew then, when we compared this to the theoretical quantum metrology bounds that you mentioned at the start of this podcast, the Nagioka bound, when we compared the measurement accuracy we can get from this numerically optimized circuit, we saw that it matched exactly the Nagioka bound, and so we knew that this circuit worked perfectly. I don't really have an intuitive reason for why a simple C0 wouldn't work. Only that it's a C0, a one entangling operation. Sorry, I started using the word C0 there. The C0 gate is the entangling gate, the gate that connects to
this
qubit.
one, right?
Yeah.
Oh.
If I just put a single C0 gate between these 2 qubits and then measure them, that's a very specific 2 qubit measurement. Whereas when we numerically optimize a circuit of the form in F, we're sort of spanning all possible 2 qubit measurements, and so we're guaranteeing that we'll pick out the best one. So the only reason I can say that is that a single C0 would be a sort of subset of all possible measurements, and so you might not expect it to reach the optimal measurement.
Mhm. Okay, okay, fine. Is that so for the, if we just, I want to go to the results, but given that this point is quite interesting, for the three copy measurement that you did, would you be able, like you said, you mentioned briefly in the beginning that you were not able to do that in an idealized way, or you weren't able to get the maximum amount of theoretical accuracy that you could technically get from that kind of measurement. Is that largely due to the circuit that you had in place that isn't working
Um,
like in a perfect way, or is it more just problems with having three qubits in the same system?
so there are a few different reasons. One is that as you increase the number of qubits and you try and implement some arbitrary operation on more and more qubits, you get exponentially more parameters to optimize, and so it becomes harder to optimize the circuit. And so possibly what was happening when we tried to optimize our three qubit circuits were that um, we weren't actually finding the optimal circuit. We were finding some sort of locally optimal circuit, and that didn't reach the three copy Nagioka bound. But it turned out when we went to so these measurements, we could have performed these measurements using an additional qubit which doesn't have the information encoded on them, and that kind of gives you just a bit of extra degree of freedom to play with. And so when we considered the, in theory, this is when we looked at performing a measurement on three copies of the qubit state with an additional qubit which doesn't have the information encoded on it, we actually found a circuit which, in theory, reaches the Nagioka bound. But when we implemented that on the actual quantum computers, the results were quite poor. It was simply too noisy. Um, to get meaningful correlation between the input rotations and the output rotations. Um, and so yeah, in practice, the three qubit measurement didn't work.
Okay, okay, understood. So then let's quickly also transition to the results. Let me see if I can find, I think, the main graph here.
Mm.
So I want to talk about this one a little bit before we close. And you have, I think, the most relevant comparison, or the most interesting one is, I would say, for the trapped ion and photonic ones. But if there's something I missed in these graphs, please correct me. So on the left-hand side of all of these, we have a lot of different superconducting architectures.
Yes.
Then we have the trapped ion one and the photonic one. And I
Yes.
think if we start with the graphs at the top here, they compare the minimum MSE to the mean MSE. Can you just give some intuition why there's a discrepancy between those two quantities?
Yeah. This is basically because modern quantum computers are not perfect. So I think a lot of these devices maybe have, somewhere between 5, 6, 7 qubits, maybe up to a maximum of 20 something qubits. Um, so even a device with 5 qubits, maybe now it's a little bit better, but a few years ago, if you had a 5 qubit device, it was reasonably likely that at least one of them qubits would be quite noisy. And so if I perform this measurement using all possible 5 qubits and all pairs of the 5 qubits, at least one or two of them measurements is going to be quite likely to be quite noisy, compared to when I use the best pair of qubits, which might actually get close to the theoretical limits. Um, and so that's basically the reason. Most quantum computers nowadays have at least one or two bad qubits and maybe one or two bad connecting gates, and so it's just hard to get good results with them.
Mhm. And for trapped ion and photonic ones, are they just more reliable in general, or how come we don't see the same
Um,
kind of behavior here, at least for the single copy measurement?
so I know this is a little bit of a moot point in the trapped ion. So a superconducting a superconducting quantum computer has a fixed number of qubits. It's a chip with the qubits. They're physically always there. The trapped ion quantum computer, you can change the number of qubits you have depending on how many ions you load into your ion trap. And so to get the best results with the trapped ions, we actually only ever loaded the number of qubits that we needed. And so the mean and the minimum are exactly the same because we only used one one qubit. So yeah,
Right.
minimum equals the mean. Yeah.
Okay. Yeah. Okay, that's understood. If we compare the trapped ion and the photonic ones between single copy experiments and two copy experiments, is there a reason why trapped ion is well? Is there a reason why trapped ion has so much higher MSE in the second measurement or in the second measurement
Um,
setup, and why photonic ones doesn't have a measurement here?
yes. So the photonic one is the easiest. The photonic quantum computer that we were using was a single qubit quantum computer. It was not possible to perform these two qubit measurements using that device. Um, so essentially, a single qubit photonic quantum computer is a single photon source with some wave plates and a photon detector, two photon detectors at the output. So it's quite a simple. Well, it's not. It's conceptually simple. It's not at all simple to set up or use, but it's conceptually simple. The trapped ion device is actually the results here are very misleading. The exact same trapped ion quantum computer has got really incredible results over the past few years. They've published multiple Nature papers, getting really good measurement sensitivities. They've done error correction. Um, but just when we were actually using the device, they were having a whole host of problems. It was, I think, a very unfortunate time for them. They really just were running into new technical issues every week, and so this was the best data we could get out, and we just decided to publish it at that stage. But I'm certain that if we went back to when their machine was perfectly functioning, they would be right down at the theoretical limits.
Okay. So probably what you would expect is if you redid this, the trapped ion in the two copy would be as low or perhaps even lower than in the single copy one for MSE.
Yeah, yeah.
Okay. Okay, cool. If we now look at the second part of this graph, so the bottom part here, where we also have error mitigation
Hmm.
as part of the graphs, can you explain briefly how that error mitigation is performed?
So the error mitigation that we use is really, really simple. It's essentially just a calibration. So what it happens is we put in a range of known rotations. Just say minus 0.1 radians up to 0.1 radians, and we plot the known rotation against the measured rotation. And what we observed before we did any calibration, what we observed was that there was a constant offset. All of the values that our measurement circuits were predicting were I'm not sure of the exact numbers, but for example, zero point 0.1 or zero point 0.2 or zero point 0.01 radians below what we expected for the angles that we put in. And so our calibration process essentially amounted to working out that bias, that offset, and then rerunning the circuit with the bias built in to the circuit. Or sorry, not into the circuit, into the estimation procedure.
Mm-hmm.
And that let us get rid of you can think of this as just removing systematic errors,
Mm-hmm.
and so it lets us
Okay,
improve
and
results.
and that also then explains, I think, what we see here, for example, where there's one observation where the error mitigation actually increases the MSE overall. I guess if the
Um,
calibration that you perform is not, or am I reading the
yeah,
graph incorrectly?
no, yeah,
Aha,
you're
sorry.
right. Yeah, the calibration probably just wasn't perfect, or yeah, it could be some sort of issue. But in general, yes, we would obviously expect this calibration procedure to help. If you look at the cases where the calibration or the error mitigation doesn't help, it's all cases where it's already very close to the theoretical limit shown by that dashed red line. And so that also kind of hints as to why the calibration didn't help, because very little calibration was needed. And so maybe if we had done no calibration, sorry, as is shown, if we did no calibration, it actually works out slightly better.
Mm,
Um, so that sort of explains it. But in the graphs where the error is much larger, you can see that the calibration helps quite a lot.
Mm-hmm. Okay, understood. I see that we're rolling up on time, so I need to let you go very soon. But just in terms of the research that you now concluded and sort of next steps forward, are there any new avenues of research that you think this opens up for, that you are looking at potentially investigating in the future, or that you would advocate that other people look into as well?
Yeah, I mean, I personally think this whole avenue of collective measurements, um, and what they can do outside of quantum metrology is super interesting. So there are so many fields that we know that they can help with, and we're only sort of now at the stage where we can start to experimentally investigate that. And a lot of theoretical work has been done on this, but still maybe not as much as in other areas of quantum information. And that's something we've actually recently put a preprint out about. We took very similar circuit structures and we applied these collective measurements to the problem of state discrimination, which is essentially I give you one of two quantum states and I want you to guess which one I sent you. So we showed that collective measurements can help with that problem. And other problems are, how can we, on a hardware and on a software side, can we improve the measurements that we did in this paper, for example? Like, there's an Australian company called Q-Control, which optimize the different pulses that are applied to quantum computers in an attempt to make them more accurate. So one of the things we're looking at is to try and implement that in this sort of a setting. So there's a lot of things to be done. Yeah, it's an exciting time.
Awesome. For people that want to get in touch with you, maybe for just questions on your research or potential collaborations, how would they get in touch?
My email is on this paper. We can put it in the description, but my email is best. Is that possible?
Yeah, sure.
All right.
All right, perfect. Then thank you very much for joining. I really appreciated the
Thank you for having
conversation,
me.
and thanks for answering all my questions.
No problem. Thank you, Nicholas.